channel. Today we're gonna work on the question all path from source to target. It's a medium level question and the question states, given a directed acyclic graph DAG of nodes labeled from 0 to n-1, find all possible paths from node 0 to node n-1 and return them in any order. The graph is given as follows. Graph I is a list of all nodes you can visit from node I, i.e. there is a directed edge from node I to node graph ij. So let's look at the example 1. There's 4 vertices, 0, 2, 3, and then the graph is basically like, I think, a adjacency list. So on a zeros index, you can see 0 connects to 1 and 2, which is seen here. And then 1 is connected to 3, so here. And then 2 is connected to 3, so here. And 3 isn't directed to anything, so it has an empty list. The output should be since it's from the 0 index to n-1, so 0 to here, we need to see all the path from 0 to 3. There's 2, right? So there's 0, 1, 3, and then 0, 2, 3, as we can see here, which is correct. And let's look at example 2. So the graph is here. It's represented like a adjacency list. And then let's look at the output. So it should be all the path from 0 to 4. So 0 can directly go to 4. And then 0 can go to 4 from 0, 3, 4. And then it can also go from 0, 1, 3, 4, which is also like these ones are here. And then there's also 0, 1, 2, 3, 4. And then there's also 0, 1, 4. So 0, 1, and then directly to 4 here. And looking at this problem, we can know that we can solve this through a simple DFS. And yeah, let's start writing the code. So first of all, let's determine what's our destination we want to go to, the end node, right? The end node should be the length of the graph minus 1, since this is a zero-based index. It starts from node 0, so when there's 4 nodes, the last node is actually n-1. That's why we're doing length of graph minus 1. And then we can start writing the DFS. And the DFS will take a node, and then I'll take a path, and then a result. So since it's a DFS, we need to determine base case, right? So for our base case here is when node equals the end node. So if node equals end node, that means we've reached a path where 0 leads to 3. And what should we do here? We should append that path to the result, right? So result.append the path. And if not, we will continue to search in our path. So for neighbor in graph node, we can do a DFS on our neighbor. And then this DFS takes in the node a path. So the path will be itself plus the neighbor, right? Since it's choosing this neighbor. And then the result will just be itself. The result only appends if we find a path from the start node to the end node. So yeah, and then we can create result as an empty list in the beginning, and then we can call our DFS with the start node should be 0, right? And then we can have a path that has 0 in it first. Because we're not appending 0 in the beginning, we're only appending the neighbor here, so we can have 0 as initialized as our path, because it has to start from the start node. And then the result will just be an empty list. And then in the end, we just return our result. this is pretty much the code for our DFS for this question, all path from source to target. Let's talk about the time complexity. The time complexity is a little bit more complicated. I would say it's not as direct. So the time complexity is actually n times. There's n nodes times 2 to the power of n. Sorry, this is times. And where n represents the number of vertices, and then 2 to the n represents the max number of possible paths from any start node to end node. From start to end node. Let me put this in two separate lines. So and why is it 2 to the power of n? Let me direct you to this solution complexity here. They solved it using another way, backtracking, but the complexity is the same. So if we look at here, if we just have a start and end node, just 2 nodes, originally we just have one path, right? One path here. But if we do add a new node here, then how many paths do we have? We have 1, 2 paths to the end node. So it states that if we continue to add nodes to the graph, one insight that every time we add a new node into the graph, the number of paths would double. So this is very important. It doubles each time we add a new node. So a new node, when we add it to the graph, the possible path doubles. That's why we do 2 as our base to the power of n, because there's n number of nodes. Actually, to be correct, based on this question, it's going to be n minus 1, but because we're just doing a rough complexity, it simplifies to 2 to the power of n. And yeah, if we look at this, we add another new path. It keeps doubling the result for the max number of paths each time. So that's why 2 to the n minus 1 as the result simplifies to 2 to the n times n as our possible path. And then for my space complexity, it would just be on, where n represents the number of vertices, because the max depth of our recursive call stack here, is going to be the depth of the number of vertices we have in the graph. So that's why the space is n. Thank you for watching, and let me know if you have any questions. Have a great day.